The last set of reactions that we're going to do in chapter 21 are the reactions of the nitriles. And when we first started chapter 21, I included the nitrile with the whole list of carboxylic acid derivatives, even though the nitrile functional group is a carbon-nitrogen triple bond. It does not have the carbonyl, carbon-oxygen double bond, like all the rest of the carboxylic acid derivatives. So initially it kind of seems like it doesn't make sense for the nitrile to be a carboxylic acid derivative because it lacks the carbonyl group. But what you're going to see is that it does the same types of reactions as the other derivatives, so it actually does make sense that it's included with the other derivatives. So we're going to start by looking at how to make the nitriles. And we're going to look at two different ways to prepare the nitrile. First of all, like the other carboxylic acid derivatives, we can convert one derivative into the other. So we can use an amide with our thionyl chloride reagent, and that will actually take us straight to the nitrile. So again, we always want to be careful with these reactions that we're paying attention to where the carbons are in this reaction. Very easy to lose carbons in the nitrile reactions. You have to be very, very careful because at this point you have done so much work with line structures that you are not used to seeing carbon represented with the letter C. So it is very easy for students, like let's say that we had this molecule right here, and you were asked to predict the product of this reaction. A very common mistake would be for students to give this as the product of the reaction, because a lot of students are not even processing the CN as containing a carbon atom. They just don't even see it anymore. And in that, what just happened right there is that I started with 2 carbon atoms and I ended with 3 carbon atoms, which is no. Don't try to not do that. Don't add carbons. But like I said, it's very easy to add the carbons in these reactions. So be really, really careful. Count your carbons. This is going to look funny as a line structure. Let's see what I did here. 1, 2 carbons, 1, 2 carbons. Didn't add a carbon. So that's one way for preparing the nitrile. The other way that we can prepare the nitrile is with just an SN2 reaction. So we could have some sort of alkyl halide or something with a good leaving group. Because the nitrile group is a pretty decent nucleophile, we can go ahead and do an SN2 and make a nitrile that way. So let's make a note that this is SN2. So that means that our alkyl halide cannot be tertiary, otherwise it will not work. So as far as the reactions of nitriles, we can get them to do hydrolysis reactions. They can do both acid catalyzed and base catalyzed hydrolysis. And the acid catalyzed hydrolysis, just like with the other carboxylic acid derivatives, hydrolysis is producing a carboxylic acid. In the acid catalyzed reaction, we're using H3O plus, and we need a little bit of heat, just like we did with the amides. And we're going to get a carboxylic acid, and I'm going to remind you again, be careful with your carbons. That nitrile carbon ends up right there, the carbonyl carbon. Now that looks like super magic, but I'm going to show you the mechanism, and you'll see it's really not that magical. It's just really cool. The base catalyzed hydrolysis all hydrolysis reactions of derivatives, all the hydrolysis reactions of the carboxylic acid derivatives are giving us carboxylic acid products. In the base catalyzed, this is just like with the amide. We start with hydroxide, and that is going to make a carboxylic acid initially, but the hydroxide will deprotonate the carboxylic acid. So that means that we need to have a step 2 with H3O plus to put the hydrogen back on the carboxylic acid. And also looks like magic, but I'm going to show you the mechanism because it's really cool. But first we're going to look at a couple other reactions. The nitriles will react with Grignards. This uses only one equivalent of the Grignard. I'm going to call it R prime so we can keep them straight. And it's just like a normal Grignard reaction. So step 2 is going to be with H3O plus or some water, and it makes a ketone. You might be thinking, what kind of witchcraft is that? Because ketones are actually reactive towards Grignards. But I'm going to show you the witchcraft because it's really cool. After I get through this last one, reduction to an amine. Using our strong reducing agent, lithium aluminum hydride, we need excess of that reducing agent and follow it up with water or some dilute acid, and you are going to make an amine. Don't lose your carbon. So your nitrile carbon ends up right there, and this is just adding hydrogens across the carbon-nitrogen triple bond. I'm going to go back and don't lose the carbons for these other reactions. So the reduction to the amine is the only one that probably doesn't seem like some kind of crazy thing is happening. The other three, though, the 2 hydrolysis reactions and the reaction with the Grignard, they're really cool. So let's look at the mechanisms for all of these. We're starting with we're going to go backwards. So I'm going to do the Grignard one first and then work my way through the hydrolysis. The Grignard, this is just going to be kind of a pseudo mechanism, not a true mechanism. And again, the reason that the Grignard reaction looks mysterious is because it ends up producing a ketone, and we know ketones to be very reactive towards Grignard, so it seems impossible that the reaction could produce a ketone. Instead of the ketone should react again with another Grignard and make an alcohol. And I'm going to use actual molecules, not generic molecules. And I don't need to do the one part because we're doing a kind of a mechanism. So the first thing that happens with this, and remember the Grignards behave like an R-, just kind of like what you would expect, the Grignard attacks the nitrile carbon because we don't have a carbonyl carbon, and it opens up that carbon-nitrogen triple bond to turn it into a double bond. And we are adding the Grignard to this. So this, if you recognize it, this is our friend, the imine. And the imine is not reactive with Grignard. So the reaction is going to stop right here. Grignards are not going to be able to attack that imine carbon. The reaction is just over. In the step 2 of this Grignard reaction, where we use H3O+, normally in a Grignard reaction, when we're using H3O+, it is because we have gotten ourselves to something that looks like this, and we're going to use H3O+ to protonate. So that's normally what the step 2 is doing in a Grignard reaction. In this particular Grignard reaction, the step 2 is doing hydrolysis of the imine, which is something that we covered in chapter 20. And it hydrolyzes it to the ketone. By the time the ketone is formed, there's no Grignard anywhere left at all in our reaction container, so we don't have to worry about any kind of interference. So that's super cool. That's one. Let's look at the base catalyzed hydrolysis mechanism next, because this one is really fun. don't know why I'm sorry that I keep making everything turn yellow. Base catalyzed hydrolysis. Now I find this mechanism to be this is a very calming mechanism, which is perfect for a stressful time. Like, I don't know what time it is that you're watching this video, but today is April 5th. So in the base and I hope that whatever day it is that you're watching this video, that we're allowed to go outside freely and that this insanity is over. So base catalyzed hydrolysis starts like a normal reaction. We're attacking the nitrile carbon and we are opening up the carbon-nitrogen triple bond, and we are making a carbon-nitrogen double bond. There's going to be a lone pair of electrons on the nitrogen, and I'm sorry, 2 lone pairs of electrons on the nitrogen and a full-on formal negative charge, and that OH group that we just added. And this reaction is done in aqueous solution, the aqueous sodium hydroxide solution. So we have some water present, and the water can be used to protonate that nitrogen with the negative charge. So that's going to take care of that problem. When that is done, so when we do that protonation, the loss of the hydrogen from the water molecule is going to leave us with a hydroxide, an OH minus, and that hydroxide, and this is going to seem kind of weird, that hydroxide is going to deprotonate the OH group on our intermediate, and that is going to leave us with this guy. There is 1 lone pair on that nitrogen. It's going to leave us with this guy right here, which looks really wild, but this molecule has a good resonance structure we can draw. We can move a lone pair of electrons from the oxygen down to create a carbon-oxygen double bond and move the carbon-nitrogen double bond out onto the nitrogen. So that's going to give us this resonance structure, and that now we have a full-on negative formal charge on the nitrogen. We did, when we were up here in this step, we protonated an OH, so that gave us another water molecule to work with, and that water molecule will go ahead and protonate that negatively charged nitrogen, so it'll take care of that. And we now have an amide. That amide is also hydrolyzable. We didn't look at the mechanism when we were listing up the amide reactions, but get ready, here it comes. The hydroxide is going to attack the amide's carbonyl carbon, open up the carbon-oxygen double bond, and we have created a new bond to an OH group. That carbon-oxygen double bond is going to close back up, and we're going to kick off an NH2 leaving group, which is honestly probably the world's worst leaving group out of all. That is a crazy strong base, like insanely strong base. But this reaction still happens anyways. Remember, we're giving it some heat, we're sweet talking it, we're playing nice music in the lab, trying to convince this molecule that it wants to react. And here we are, and we're almost done. And now we are, when we write this reaction out, let's scroll up and find it. We are now right here, step 2, add some H3O plus, or I'm just going to use water and protonate that carboxylic acid. if we're doing this actually in the lab, we'll get better yield if we actually use an acid for this last protonation, but we always get 100% yield on paper. So there's that mechanism. Isn't that thing awesome? The last one that I want to show you, the last nice soothing mechanism for you, is we're going to do the acid catalyzed hydrolysis mechanism. Now, I always find the acid catalyzed reaction mechanisms to be a little less fun because they do feel like they have more steps to them.